Hello, today I will talk about econometrics and economic data. The outline of this presentation is first to define econometrics, economic models, and econometric models. Then I will define the types of economic data, including cross-sectional, time series, pooled cross-sections, and panel data. And finally, I will talk about causation versus correlation or relationships in econometrics. So, how do we do econometric analysis? We typically start with an economic model, though not always, and then we estimate an econometric model. And oftentimes, again, the first step of defining an economic model is skipped and we go straight into an econometric model. And I will show you examples a little bit later on. So, what kind of economics models do we have? Well, we can analyze micro or macro variables. We can estimate relationships between different economic variables. For example, we could be working on supply and demand models, or as is common in finance, we could work on pricing models. So let's provide a few definitions. First of all, what is econometrics? That is the use of statistical methods to analyze economic data. So again, we have economic data, and again, we'll talk about what economic data is. And we use a specific type of statistical methods to reach some conclusions about what kinds of trends this economic data provide us. So different type of econometric models are used in economics, and these are basically the statistical models that are used in economics. So we have a fancy name for these statistical models. We call them econometric models. They basically specify the relationships between the variables. So we typically have one dependent variable, the variable that we try to explain, and several independent variables. So that is true across most models that we will talk about later on. So we can use econometric models to, first of all, estimate relationships between economic variables. So we want to know how do two variables relate to each other. And then we can also test economic hypotheses or theories. For example, do new taxes increase the prices of houses or reduce prices of houses? So that's an economic hypothesis that we can test with real life data. We can evaluate the effectiveness of new policy. For example, if people receive food aid, are they more likely to uh, have better economic and health outcomes? Or we can forecast economic variables in the future, such as we may try to have a prediction about what crop yields are going to be next year based on data from previous years. So here is an example of an economic model that describes determinants of wages or salary for, say, U.S. workers. So the notation that we will use here is wage equals F, where F is the unknown function of education, experience, and training. So this means we have independent variables such as education, experience, and training that we're trying to use to explain how does wage vary with them. And F, as of now, is this unknown function that relates these variables to the dependent variable wage. Or more generally, we can use y equals f of x1, x2, and x3. So y is again the dependent variable, the one that we're trying to explain, and x1, x2, and x3 are the independent variables that are explaining the dependent variable. So here is a specific type of econometric model where we know the functional form. And this one is basically a linear regression. So here we have wage equals beta 0 plus beta 1 times education plus beta 2 times experience plus beta 3 times training plus U. So here the functional form is specified. That's the multiple regression model that we will talk about later on. More generally, we can define this as y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus u. Here, y again is the dependent variable that we're trying to explain. x1, x2, and x3 are independent variables. Beta 0, beta 1, beta 2, beta 3, these are the coefficients that we will be estimating with the econometric model. And U, that is an error term that represents all the unobservable factors that affect our dependent variable Y. So basically, everything that is not captured by X1, X2, and X3 are going to be put together in U. That is the error term, the factors that we are unobservable and not captured by this model. So notice here that there's a correspondence between the model that we have above here that is a little bit more specific and the model that we have below here that is a little bit less specific, kind of more general interpretation. So this x1 is how we denote the variable education. X2 is how we denote experience, and X3 is how we denote the variable training. Um, and these beta coefficients are capture the effect of a variable X on the dependent variable Y. That's how we are going to be interpreting these coefficients that we will be estimating. So, what are the goals of an econometric model? So, after we estimate and find these coefficients of beta 1, beta 2, and beta 3, we can test different hypotheses. So, for example, what is the effect of education on wage? That is represented by the coefficient beta 1. And we would be trying to estimate this coefficient. We would also test hypotheses such as, is beta 1 significantly different from 0? Or is it basically the same as 0, not significantly different from 0, meaning no effect? Or do we have a significant effect? And then we can also look at the magnitude of this beta 1 that we are going to be estimating. And we will try to kind of make an inference, is that economically large effect, whereas this is a bit more of a subjective interpretation. Basically, how big is this effect of education on wage? So now moving on, let's talk about the different types of economic data that we have. Um, so this economic data will be used by our econometric models. And these are the types of data that we will talk about. Cross-sectional data. So this is across people or units. Time series data would be usually over time. Pooled cross sections would be over 2 or 3 or more time periods. And then we will talk about panel or longitudinal data where we have both people or units and time. And which type of model we use really depends on the type of data. So we first need to start by assessing what kind of data we have, and then we will apply the appropriate model to it. So looking into cross-sectional data, so this would be data for people or households or businesses or countries or cities and so on. So this would be the cross-sectional dimension of the data. So the data would be at a given point of time or during a given period, but there's no time dimension. There won't be multiple time periods in this type of data. And we would typically denote the individual by I, although you can use another notation, but that's typical one, I. And we need to keep track of uh, which observation we are talking about, and that's going to be the individual I. And this type of data, cross-sectional data, is widely used in microeconomics. So we will see a lot of examples for this type of data later on. But here's one example. Here's cross-sectional data on wages. And this would be a wage or hourly wage. And these would be the observations. I pulled up the first few rows of the data for you to see here. So here, y I would be the dependent variable wage. And then if we want to estimate an econometric model, we could have several independent variables such as education, experience, tenure, how many years on the job, whether or not the person is female and married. Likewise, the data comes with another variable, which is L wage, which is typically abbreviated for log of wage. We're taking the logarithm of wage. We will also talk about logs later on in the semester, or we can have a variable squared, such as experience squared. So we are basically taking this variable here, experience, and squaring it. We can use a variable that way in the model. So note here the notation of I, Y, I, X1, I, and so forth. So YI is the value of the dependent variable for the I observation or the I row in the data or for the ith person. Now, in this data, I don't have, say, the names of the people that this data belongs to. That was not provided in the data, but I know that for the first person in the data, this is the wage. That's their education, that's their experience, that's their tenure. So this I here behind each variable denotes that we're talking about the value for the person I. Okay, and again, you can see like that different variables we would denote by x1, x2, and x3. This is more generically describing education, experience, or tenure in this case. We could have some of the variables being continuous, such as the ones you see for wage, education, experience, and tenure. Or you can have what we call dummy variable or indicator variable 0, 1. So here is if the person is female, they get a value of 1. If the person is not a female, they get a value of 0. And here, if the person is married, they get a value of 1. And if the person is not married, they get a value of 0. So we could have different types, different types of values as well, depending on if it's continuous or a dichotomous variable, just a 0, 1 variable. Okay, moving on, we can also have time series data. These data are typically used in microeconomics. They could be financial data and so forth. Typical examples here may be stock and bond prices or the gross domestic product or growth rates. The most important thing about time series data is that the observations are over time. So we do need to have a time dimension for time series data. So data could be annual, monthly, daily, hourly, or by second, depending on the data. And then there are also different types of complications for these time series, such as they may have a trend, such as rising values over time. So, for example, if you look at crop yields in the US, they tend to rise over time because of improvements in technology. They could have seasonality, such as higher values in a given month. You can think about retail sales and how they increase, say, during the month of November or December because of the holidays. Or some variables could have cycles, say, every 3 to 5 years, say, based on recession or booming the economy. We can see higher values and lower values for different variables. It's also possible that observations may be serially correlated. This means that the errors that we talked about, from before, these errors are correlated from one period to the next. So they would carry over from one period to the next. And so again, uh, we need to take this into account as we select the appropriate models for it. So here is an example on time series data, and this is of minimum wages. So here we would have year T, and here are the several years that we have in the data. Our dependent variable YT would be the average minimum wage, and then we have average coverage, GDP, and unemployment rate as, say, independent variables. So notice here that the I dimension that we had before is replaced by T because the data is not for people. So the rows here are not people like it was before, but are years. Here we have that T has to be in the data, which means we absolutely need to know which time period the data refers to. And these should be ordered, say, when you're plotting it on a graph. That is important. So here we would denote T as the time dimension. Y, again, YT would be the dependent variable, X1T, and so forth would be the independent variable. But now every observation or row is at time t, specifically at time t. So that's very important to note here. Next, let's talk about pooled cross sections data. And what we mean by this is that we can have data where we have the house prices, say, of houses that were sold in two different periods, say 1 year and then another year, but not the same houses are sold every year, right? So we have different houses that are being sold in different years. So again, we have data over time, but it's not necessarily for the same unit, for the same house. So here these cross sections are drawn independently from each other. And this kind of data can be used to estimate the effect of a new policy. Say, what would happen if we have a new tax imposed on the house prices? Would the house prices increase or decrease? Here's how repeated cross-sectional data looks like uh, for, say, house prices. Here we have a T dimension and we have all the house prices for the, say, before period and all the house prices for the after period here. And these are the house prices. And again, we're not talking necessarily about the same houses being sold in 78 and 81. It could be different ones. And so here we can talk about the model where the house price depends on how many rooms does the house have, how many baths, and so on. This variable is the logarithm of the price variable. And one variable that we can create that's very important in these models is the dummy variables, where we can say equal to 0 if it's in the before period and equal to 1 if it's in the after period. We would use a variable like that a lot. So here again, we have every observation is at time t. We absolutely need to know uh, if the observation belongs in the before period or the after period. So here again, our y would have a t dimension and our x's would have t dimension in them. And finally, we would have panel data, or also called longitudinal data. And for example, we can have employment data across individual and over time. So for example, we can have the salaries of people across different years. This means same people followed over time, over years. So we have multiple years for them. So the most important thing to note here about the panel data is that we have the same cross-sectional units over time. So this data set has both the cross-sectional dimension I and the time series dimension T that we talked about before with cross-sectional and time series data. So here's an example of panel data on wages. So here we have a person ID, so person number 13, person number 17, and person number 18. And so for these people, we have 3 years of data for 80, 81, and 82. And this is an example of perfectly balanced panel data, which means all the years are here for all the observations for all the people. So we have balanced data. Sometimes a year, say, could be missing for a certain individual. So here we have log wages. We can try to explain log wages with experience, education, and how many hours they worked. So notice here that we have I, T, and for the dependent variable, we have YIT. So we have both indices here denoting not, not only the I dimension, but the T dimension of the data. So again, that is very important that the panel data has both I and T dimension to it. And when you talk about this particular value, for example, this value, we need to say that this value belongs to an individual 17 in the year 1980. So we need to say both the I and the T dimension when we refer to a value. That's why each of the variables has an I and a T index behind them. Okay, so these were the different types of data that we have. Now let's talk a little bit about causation versus correlation. So here we would have causation. If we say an additional year of education causes wages to increase by a given amount, all else equal. Or if we just have a correlation, we can say a weaker statement, which is an additional year of education is associated with higher wages. And so for most economic study, a causation cannot be determined. It's only a correlation. So saying that is associated with as a better practice than saying causing when we interpret, say, regression results. So let me just give you 2 examples of causation versus correlation. So here we can talk about causal effect, say, of applying fertilizer and what would happen to the crop yields. So we're interested in the question, will crop yield increase significantly if fertilizer is applied? So an implicit assumption in all of that is that we hold all the other factors that influence these crop yields constant, such as the quality of land, the rainfall, and everything else being held constant. So here in this example, we can uh, choose to have an experiment where we select several plots of land and we randomly assign different amounts of fertilizer to the different plots. So for example, this plot would get less fertilizer, this plot would get more fertilizer. And then we can record what the crop yield is for these 2 plots, and then we can compare the crop yields and say, does actually putting more fertilizer on the land increase crop yield? So that's a valid experiment because the way we apply the fertilizer is not related to any other factors influencing crop yields. So in this case, we truly could have a causation of applying more fertilizer, leading to higher yields or not, depending on what the results of the study say. But in observational study, we don't have these perfect designs in experiments, so we only have observational study, which means we observe plots that have different level of fertilizer and different levels of yield. So if there's a positive correlation, let's say plots that have more fertilizer are shown to have more yields, does that mean that applying more fertilizer will result in higher yield? And the answer is no, it doesn't mean that way because that's a correlation, not a causation. It could be that other factors affected that crop yield as well. Maybe more fertilizer was applied to land that already had higher productivity and the soil was richer, and that's what caused the higher yields, not necessarily the application of the fertilizer. So we just have a correlation if we look at an observational study, not the causation. So here is again an example of correlation and how we cannot interpret that as a causation. So what is the effect of education on wages? So we can be interested in the following study. If a person at random is given another year of education, by how much will his or her wage increase? Here again, we have an implicit assumption that we hold all other factors constant, such as experience, ability, and so forth. So if we're trying to have an experiment here by assigning people at random, you get to have another year of education. You do not get to have another year of education. That's typically not feasible because, well, it's kind of hard to have this experiment in real life. So there's a problem with this kind of random assignment because people that actually choose to have higher education uh, that choice may be related to other factors that influence wages, such as, say, their general level of intelligence. So in an observational study, we only observe what the education people have and what wages. So all we can say is that people with higher wages have people with higher education have higher wages, which is a correlation. But we cannot say that if a person gets additional education, they will get higher wages. That's causation because we don't have that kind of experiment in place. We only have observational data. So with that said, these are the questions that you can take a look at to see that you understand the material well that I just presented. And with this said, I will see you in the next video.